All right, welcome everybody. And it's been a while since I posted, but this is a really good example project of how you can really take advantage of free and open source software technologies, especially in the arena that a lot of folks have been calling the low code as a platform environment, to really do some very powerful capabilities and help not just you as an individual developer, but your organizations get away from current vendor solutions so that you do not feel like you have to continue buying down the vendor rabbit hole and essentially get stuck in the solution stack that they wish to sell to you. And in today's example, we're going to cover an implementation of tracking OEE using a Arduino Uno Wi-Fi microcontroller, and it's hooked up to a toaster that is sensing the current via a split current transformer, and it's streaming the current values as flat MQTT, and the visualization is actually done over Streamlit. So with that, let's go ahead and break down some of the things we're going to cover today. So in this project, we're just going to cover some of the motivation for why a architecture diagram, just to let you know where each of the bits of technology fit in play. I'll show you a electrical schematic for the circuit connections, and I'll explain some of the electronic theory and design that went into how it was designed. I'll have a full parts list breakdown, as well as a physical wiring diagram showing you how I physically wired it, in addition to the software schematic that you'll see. We'll go through a short code review I've already uploaded to GitHub, and I'll talk about some of the code design architecture and why. And we'll also talk about some optimization and future steps, give you an overall summary, and right there on the bottom, you can see a link directly to the GitHub repo, and this material will also be readily made available to you, this entire slide deck. And before I forget, nobody paid me to do this project. Nobody reviewed it before being published. This is all my own original work. And frankly, I actually took the initiative to see just how much of this I could do purely out of using straight GPT, where if I were to put myself in the shoes of a complete novice developer who had no real understanding of the pub sub or broker technologies, about microcontrollers and so forth, just how far could I get? And it turns out you could actually get very, very far. So without further ado, let's go ahead and talk about some of the motivation for the project. Basically, I actually came across a video, and it was demonstrating how you could track machine state using the Tulip platform, which that platform can do a lot. But in today's day and age, where there's so many open source technologies and so many open architecture platforms, that I think it's high time that we really start seeing not just developers, but even organizations get away from any vendor lock-in and essentially be able to empower not just their employees, but also to be able to allow other organizations to help each other build truly digital pipelines and infrastructures in order to be able to have direct transparency and immediate real-time access to what's going on. And ultimately, what that allows is better use of resources, making sure that priorities are set straight to provide more value, to work on projects that are bring more value, and to really push the boundaries and innovate more on some of the existing technologies, as well as uh, discovering new technologies. And with the launch of public LLMs and so many other sort of low code as platform environments, namely in the free and open source space, talking about Node-RED as an example. You can really do quite a bit that you otherwise in previous generations would have had to rely on purely pay-to-play platforms. And it also turns out that a lot of the free and open source alternatives are, although a little more involved in what you can do straight out of the box, it turns out that ability to really change and configure what's under the hood directly rather than having to go through some GUI interface and remembering drop-down menus and configurations and so forth is way quicker than somebody that would have to rely on a vendor product like a Mendix or even like a platform like Tulip, for example. And so really, I just wanted to see if I can do it, more or less as a free alternative, and you can. And a lot of the things that I built out in this project, you can actually take as and modularly utilize in other projects, particularly the timeline feature that you'll see that shows a simple single bar chart oriented horizontally that timestamps when the first off condition state was made. So yeah, I was really just wanted to see if I can make a free open source alternative to Tulip and other such low code as platform environments, and using purely open source technologies. So before we get into some of the technical details, I just want to take a major step back when we're talking about electronics. There's many ways to wire things. I chose the path of least resistance. There is a pun in that. And basically, whenever you take a look at a breadboard, what you actually have are metal bars that run horizontally, and then you have these vertical rails, and everything that is connected horizontally on the rows is connected together. Everything, in this case, that's connected vertically is connected together. So if you were to take any breadboard and you remove the backing, this is what essentially you would see. And it's important to know how the metallic connections are made, because that is what goes on behind the scenes where you connect your jumpers and so forth. So I always like to include this as a good reference. Frankly, I forget a lot of times. In any case, let's go on to the actual schematic. So this is a schematic of the setup. You have your wall power, 120 volt AC, since I'm in the States. You have your toaster, and essentially it's just a switch where the front of the dial, and you'll see photos in a little bit, you turn clockwise and it's timed. That switch will stay on until eventually a spring releases it and disengages after a certain amount of time. That time is based on a set of physical properties of the spring that's holding the knob together, and that's how the knob eventually releases to then allow for a open circuit. And you have a split core transformer, and this is what it's doing our current sensing. And I'll talk a little bit about why this isn't necessarily a perfect way to measure what the current is. But basically, you have one of the inputs of the current transformer going to the analog input of the Arduino, and then the other tied directly to ground. You don't have to tie it to the A0 input on the Arduino. On mine, I believe it has 7. This is just the best schematic symbol I could find, and I'm using KiCad to make this schematic here, which is also, again, free and open source. So mine has 7 analog inputs. Some other Arduino boards, you could use those just as well. They might have 5. And really what you're getting out of this is, if you choose to go with the Uno Wi-Fi, and I know this says Uno R3, but it's actually the Wi-Fi version, you have a Wi-Fi chip directly built in. and as well as a analog to digital converter. So that's why I chose the Wi-Fi. I can directly program the board to have direct connection to my network. So what did I use? We used a Arduino Uno Wi-Fi Rev 2 microcontroller, a manual switch operated toaster oven, a small mini split core current transformer, one breadboard, two jumper cables, as well as the male USB-B to male USB-A cord in order to connect the Arduino to my computer, so I can upload the sketch, which is essentially just C code, onto the Arduino, so I can do what it does. Next, the physical wiring. So this is the split core transformer itself. Very basic, positive and negative lead. This is the exact board I'm using. And you can see on this side, mine does have the additional inputs, but this is where your analog in would go, and you can use any of the ground. Here we actually have the toaster itself. So when you take a look at the knobs, as we're talking about manually operated, so this knob you essentially churn, and if you churn clockwise, it will again engage a different either a spring or a potentiometer, where this is the spring, and it'll depending on its properties, will stay on for a given time. These are in units of minutes. Whereas if you turn it to the left, counterclockwise, it will just simply stay on until you manually shut it off. And this is essentially serving as our switch. How we wired everything up. So I have the actual rows and columns of where the leads went here. But basically, you took the red, which is your red of your split transformer going to the analog input. You could choose any of them. I chose a 0, doesn't matter. And then the black goes to a ground. And of course, this goes to your 120 volt AC wall power. Your current clamp can go on either lead. I believe this one is the hot lead on my toaster, but essentially you can still measure your current. If you wish to not use the hot lead, you just have to do an inverse so that your triggers are set correctly when you're looking for a positive output of current. And here you can see a more close-up of where I actually place the jumpers. And of course, this is a top-down view of the breadboard schematic. And again, just to take a step back for the actual architecture diagram. So again, you have your field device, right? Your split core current transformer, which is just a current sensor. You have your edge device being the Arduino microcontroller, and as it's sensing from its analog inputs, it's transmitting those values over flat MQTT to this designated topic. This is stored directly on the Arduino itself, and I intentionally chose to have the edge device really do as little work as possible. Typically, I like to see the edge doing only just the data validation to ensure that what it's streaming is actually going out. That's all I really like to do at the edge. I don't like to do any pre-processing. If it's necessary to pre-process the data, I like to have another layer that's sitting above the edge that handles that, and that's typically done for modularity in order to prevent any sort of changes directly on the edge itself. From there, we have a pre-processing script, all built in Python, that parses the flat MQTT to a JSON object And from there, we utilize Streamlit to serve as the front-end visualization, which provides a pie chart aggregate for the percentage that your machine is on versus off, and then a horizontally oriented single bar chart that shows when the state was on and off, and when the off state is achieved, it'll show you the timestamp of when that first off state is achieved. And it will keep a track of on and off states for just the last hour to not flood and overwhelm the visualization of the timeline. So that way you're not crammed with lots and lots of data points. Some of the equipment specs, I won't go into all of them, but really what I wanted to do here is just explain some of the physics to you. So the toaster I'm using, it's able to generate 1500 watts of power. If we look at our basic physics equation, because this is using resistive elements, this toaster, believe it or not, is actually drawing a maximum of 12.5 amps of current. Flat, that you can assume is constant. And we're assuming a steady state operation, meaning that the values we're publishing do not consider any startup or shutdown phases, because there is actually a ramp up and ramp down period. Similarly, when you start your car engine, when you start a rough pump or any other vacuum pump, and most pieces of machinery really have, you do have to take into account those startup and cold start conditions. We're assuming they don't exist. It's an immediate delta from 0 to 1 being on, and then from on to off, it's immediate. But again, if you were to actually plot that, you would see that it's not as sharp. It's actually more of a curve there, and modeling that can actually be quite challenging. But in this case, we're assuming that not to be the case. And frankly, a lot of the other videos I've seen that do not really cover this type of information. They just assume that people know that all of these assumptions are made and that you are operating under certain conditions, but you really have to have this because not just as a circuit designer, but as a developer, you want to make sure you clearly articulate what assumptions you're making, what your architectural choices are, rather than just spaghetti code away and pray that things work as intended. Again, when you're talking about startup and shutdown and the path towards achieving steady state, to actually calculate the models, just to briefly touch on it, you would actually require transient circuit analysis, where you get into some deep calculus and integration to actually generate an accurate model of what's going on during these periods. Because even for this resistively operated toaster, it still does play into account. Some of the assumptions we're making on the microcontroller end. So I believe we'll touch on it on the next slide, but when you actually look at the Arduino, the analog inputs it has actually do not take measurements of current. They actually go off of voltage. And the reason why is because of how the analog to digital converter internally functions. So we're assuming that the signal we're generating in this case, being the 12.5 amps of current, does not exceed the measurement capabilities of the 0 to 5 volts range of the analog to digital converter. We're also assuming, by the way, that the transformer itself is operating in a linear fashion. Again, even though it's a resistive heating element, there are some high frequency operations that do occur at startup and shutdown. We're assuming those to be negligible. They, in fact, are not. And that the resistance is holding constant, so that we can assume a constant 12.5 amps of current. No fluctuations, even once it achieves a sort of quote unquote equilibrium state, there is fluctuations, and we're assuming those to be negligible. And that the 120 volt AC power that's supplied by the wall is always a perfect sinusoidal 120 volts AC. There's no interruptions, and that your power is clean and pure, and there's no issues to take into account there. And again, obviously, we're assuming that the highest current that can be achieved from the toaster is 12.5 amps. There are fluctuations, and so especially as you leave it for longer, not just the data generation that's happening as the Arduino is reading, but also your cabling will heat. Even though a lot of the shielding is rated, it's not rated to go on for entire days, but it's good to clarify those assumptions. And to take a step back, when I mentioned earlier that not a lot of other content explains this, so before diving into the realm of electronics, just some very basic fundamentals. The way the transformers work, you get a current output because your primary winding is passed through by the current to be measured, and then the secondary winding generates a proportional current. That's not always the case. Many times, again, we're assuming a perfectly linear transformer, but there is loss due to various factors: heat, frequency, skin effect, so on. Typically, the way you would take a current value and transform it into a voltage reading, you would actually need what's called a burden resistor circuit in order to essentially see a voltage drop, so that your A to D ADC tool, your analog to digital converter, which again is built into the Arduino I'm using, can actually detect that voltage change. Also, keep in mind, typically calibration is needed in order to tune properly to the transformer's sensitivity, and that takes the form of differently sized resistors, potentially splitting up of many resistors in series or parallel to take into account fluctuations, startup and shutdown conditions. You might wish to also have capacitors in parallel in order to deal with some of those conditions. So these are just things that you would need to normally take into account. But again, we're assuming ideal transformer behavior where the relationship between the primary and secondary voltages are equal, they're linear, there's no hysteresis, there's no magnetic saturation in the core material, which would typically happen at higher frequencies, as well as the transformer operating for some time. There's no cooling in this environment, but in industrial applications, you'd have to worry about cooling down your magnets. Again, some of the non-ideal behavior you would typically see: your core becomes saturated due to high mag flux densities. So therefore you get nonlinear input and output voltages. You would have to take into account in an industrial setting, hysteresis due to high operating frequencies. We don't have that here. We're looking at very low frequencies at 60 Hertz based on the specs I mentioned earlier for the toaster. So we can ignore it. They're not absolutely zero, but they're close enough that you can ignore it. I mentioned eddy currents. Again, typically happens at higher frequencies. Again, if you leave this running for too long, temperature will affect the core permeability. And if you change the load, which would typically involve startup and shutdown procedures, that could affect your output. So you might not necessarily get an immediate off condition being read based on how hot and how well the transformer is able to adapt. So, and you can take care of a lot of these, again, using some other circuit components, but in this case, we're assuming it's all ideal and perfect. However, in reality, you would have to take into account. And of course, you'd have to take into account how fast you wish to read this change in voltage, aka how many how much data do you wish to sample? And with that comes the ability to validate that the sampling is happening at that frequency, and in fact, it's reading correctly. So there's a lot of rabbit holes you can see just from this slide alone. You can really go down and ensuring what you're reading is actually true, and that any other non-ideal scenarios are properly being accounted for, and that they're being that you're able to validate the readings of those non-ideal scenarios. So to explain how the Arduino works, it has analog inputs. They utilize a built-in analog to digital converter. It has what's called a 10-bit resolution, where basically it represents an analog voltage as a digital value between 0 to 1023. It converts this based on principle of proportionality, meaning the ADC reading is proportional to the physical measurement, meaning it can't read current values natively. You can simulate a burden resistor in your Arduino code. It's not perfect. It does work, and therefore the current that's actually able to be measured on the analog input depends on the circuit's ability to convert the electrical current into a voltage reading. And the analog input, again, in the Arduino can only take a range of 0 to 5. So how we did this in the theoretical model without having a burden resistor is we just normalize the ADC value, and you get a fraction. Then you multiply by max current, which again we set to 12.5, and that scales the value to an actual current range. Then we essentially convert it to a string format using some floating point current, using the data string function. And that's how we're able to get a pseudo voltage reading in our Arduino without a burden resistor. Keep in mind, when you do this, you also have you do run into an issue where you could potentially damage your analog input, because number one, not only does the burden circuit serve to provide you voltage value, but it also acts as a buffer to protect your analog input from getting current values that will potentially fry the circuit. So I guess what I'm trying to say here is that I took one for the team, and I did this on my board. And thankfully, we don't have quite a need for high fidelity of data and resolution of said data. So we can assume that all is well, and my Arduino board is not broken. Thankfully, it's just an Arduino board, but you can imagine if this was a PLC, you definitely would not want to do this, because a PLC is far more expensive than an Arduino. And the Python code I'll show you here, but actually, well, let's just go ahead and dive right into it. So basically, I made a simulation that will show you the values of current being streamed out, and you will see a single bar chart and a timeline and a pie chart that's aggregating the OE values. So we'll go ahead and we'll pull up our simulator. So here we're simulating our Arduino values. I do actually have my Arduino. I'm using it for something else right now. Here is our pre-processing tool, which again, all this, don't worry about memorizing, it's all on GitHub. And then here we actually have the Streamlit app that's actually generating the visual front end. So with that being said, the first thing we're going to do is we're just going to go ahead and run the Streamlit application that's doing our front end visualization. So that just opened. And you can see here, the first off condition was met. and it captures the date time. And we have now our pie chart reflecting what percentage of time the condition of on has been met versus condition of off. The pie chart is a aggregation of all time. This is just an aggregation of the last hour. And it's all in real time. The cool thing here is using the matplotlib library in Python app, rather than having to fumble around with drop-down menus and buttons and getting this perfectly how I want in a low-code platform environment like Tulip, I can just simply tie directly into the backend to say, I want this shape, I want this size, I want this annotative marker to show up exactly like this, and bam, there it is in Streamlit. And that's really the power of a platform like Streamlit compared to a purely GUI environment like a Mendix or a Tulip. You know, the ability to just immediately on the fly dynamically implement some of these changes is so critical because you can spend so many development hours by hand trying to get all of it to work in your commercial off-the-shelf software. But why, when you can just do it on your own exactly how you need it to be? And granted, I did try using other visualization tools, namely Grafana, to do some of this front-end visualization, but the transformation of the data to have it be this, and for this bar chart to show up exactly like this, and don't mind all of the timestamps. You know, when you have simulated values and there's so many of them that are off, it's bound to get a little compacted there. But, you know, say I wanted to have nothing show up on this bar chart except for when I hover my mouse. You can do that completely and easily. Just spin up your Streamlit app script and code it right then and there. No more having to go back and forth with your GUI and commit the changes. You know, that's really the power of a framework like Streamlit. And, you know, when we talk about software development, there's so many things that go on into making truly production ready code. So when you'll see the Arduino code I made, that's the right one. Yep. You know, functions like this one where we're connecting to the MQTT broker. Well, in production, we need some robust handling of network reconnects. Are we going to limit to X number of reconnects? What are we going to do after X reconnects have been attempted? What are we going to do if it was connected, but it just briefly timed out? But somehow, do we store those values locally and then push them back out to queue? These are the types of things that ultimately you would take into account when you're doing a real production development, right? Similarly, do we instantiate a new connection to the broker? You know, are you storing network credentials locally? In the case of the Arduino, you can use a library that encrypts the network credentials to the EEPROM memory, which has a limited amount of read-write cycles, but also even if somebody had physical access to it, that data would be encrypted. Are you using just hard-coded network credentials like I did? In my case, I did so because I had a guest network setup where I could just simply secure the network at home and not have to worry about the IoT device connecting to my main network. You know, these are the types of design choices that you have to think very closely about. And then similarly, when we're talking about the Streamlit app itself, right? Say we have multiple MQTT topics. How do we wish to handle discovering of multiple topics? Do we wish to make a separate dashboard for each topic? What about the Streamlit app? Even though it's a web-based app, how do we wish to handle the connection of the app to the broker in order to pull this data from? The way I architected the app, I actually left it to purely interact with just the broker. There is no sort of buffer of storing the data inside the app itself or in some other intermediary place. I just have it directly parsing MQTT topics, and that's all it's doing. But again, of course, what if the network experiences issues? Is there a certain amount of tries? Are you going to go and potentially do a monolithic Streamlit application that is able to handle multiple visualizations, or are you just going to modularize and say, the generation of the Streamlit app we're going to handle as one service, and then the connection to network and reconnects to the broker as well, we're going to set up as a completely separate service. These are the types of things that you have to take into consideration. And you can really go down an infinite rabbit hole at this point. But in here, what I wanted to aim to do is show just a fundamental example that you can, in fact, and should go and pursue a free open source alternative to some of the commercial off-the-shelf solutions, because not only for cost-saving measures, but there's never an issue of, will this technology be around? It will. There's no licenses to pay off of it. It's just a matter of getting underneath the hood and, figuring out how your technical considerations. And so I will show you to the link of the example that I took the motivation from, right? You can see they have a similar manual switch operated. And here again, as they're showing the electrical current values, that's not a true current value. The way they had the board lined up, there is no burden resistor circuit. And I did take a current, an actual current clamp multimeter to measure the current coming out of the toaster. So it was a little under 12.5 for my toaster specs, but again, these are the types of things that I find very much lacking in a lot of these demonstrations, to really get down to the nitty-gritty details of the materials used, the architectural assumptions and design concepts, and some of the best optimization features that you could do next. So I hope this was helpful. With that, we'll end it there, and I will see you guys in the next one. Take care.